Hey guys, in this lecture we're going to be covering the Vandermonde's identity and some of the proofs, right? Okay, so the idea is very simple. We're going to cover three different theorems and each one is going to be a bit more harder than the previous one. Genuinely, this is a tricky lecture, I'll be very honest. Um, the idea is, I'll just give a quick idea of what the entire lecture is about, right? You have pretty much an equation like this for the entire lecture. Just assume that this is an equation, don't think about the identity now. So it's pretty much that you have the left hand side and the right hand side, and you're showing why they are equal, right? Okay. Now, in general, my point is that these identities are like not very important to know. The identities themselves are not important to know, but knowing the proof, knowing how these techniques work is what's important, right? My idea is that knowing how we actually came to these conclusions and these theorems is what's going to be very helpful in understanding discrete math, right? If you remember in the last lecture, we covered the proof of Pascal's identity using the combinatorial proof, right? And that's exactly what we are doing in this lecture as well. You're kind of understanding the technique of, okay, how do we actually do a proof, right? How do we actually prove these? Now, the point is, you can pretty much do this exactly this way as well. Okay, why not I just do the sum and do the algebra and come to the conclusion? Why can't I prove it that way? The problem is very simple, right? A lot of the proofs that you do are very difficult to solve or prove with algebra. And they become extremely easy when you do them with combinatorial way. Meaning you just kind of represent the left hand side and the right hand side in a way of just counting objects. And it makes things a lot more easier to understand, right? Okay, so just a quick summary once again of, I just kept on bluffing, so I'll just quickly give a summary once again. My point is very simple. These identities themselves are not important. What's important is knowing how these techniques work. Instead of proving using algebra these proofs, what you do is you show them in terms of the counting, in terms of combinatorial proof, right? Okay, if we just count things this way, then left hand side would be equal to the right hand side. Okay, so let's just take a look at the Vandermonde's identity first. So it's saying if you have C m plus n comma r, then it's equal to the sum of C m comma r minus k multiplied by C n comma k. Okay, let's just quickly understand what this is doing. The thing is, if you have something, let's say m plus n comma r, right? You can kind of separate it into two different combinations and sum them together. So I've given this example over here. So let's say you have C5 plus 5 comma 3. Now I can write m over here is 5, n equal 5 as well, and I can say r is equal to 3. Okay, so this is what I'm doing. If you look at all of these terms, I keep the value of m and n fixed, right, in each of these terms. The value I change is the value of the second point, right, the second thing. So firstly, it was 3, 0, then it went to 2, 1, then to 1, 2, and then finally to 0, comma 3. Right, that's exactly what you're doing. Okay, so the point is not very difficult to understand. If you try to sum this up together, you'll get 10.1 plus 10.5. 5 plus 5.10 plus 1.10, which will give you 120. And you can try to also double check this by solving C10 comma 3 directly. And if you solve this directly, you'll also get 120. So that's exactly what we're doing. Now, we cannot just show an example and say, okay, this works, and that's how the entire proof is. I'll have to actually show the proof of why this entire formula really works, and I'll show the animation for it. Okay, but once again, the idea is that it's more important to understand the technique of how we did the proof rather than the actual theorem, I should say. Okay, now let me just quickly show you guys the theorem. Okay, so combinatorial proof of Vandermonde's identity. Here's how the story goes. So let's consider we have two teams, right? Team A has 3 people and team B has also 3 people, right? Now the idea is we need to pick a committee of 2. So we're going to count that committee 2 different ways, right? Okay, so let's just take a look at way 1. Now, way 1 is easy. Forget the teams, merge everything into one pool of 6 people. Now pick any 2, right? That's going to be 6 choose 2, which gives us 15 committees in total, right? So 15 as a target, whatever way 2 gives us. it has to match exactly 15. Okay, now way2 is partitioned by the B count. So let's just take a look at B now. Okay, so way2 is pretty smarter, right? You need to organize those same 15 committees by how many come from team B. So a committee of 2 can have 0 Bs, 1 B, or 2 Bs, right? That's the full list. So every committee has exactly 1 B count, so each one lands in exactly one bucket, right? So watch, 2 A's goes to the bucket 0, right? 1 goes to the bucket 1, and 2 goes to the bucket 2. Okay, now count the middle bucket, right? Committees with 1A and 1B. 3A options, 3B options. Is the answer 6 or the answer 9? If we add 3 plus 9, we are pairing, right? We are pairing A1 with B1, A2 with B2, A3 with B3. So we have 6 committees in total. Now the problem is A1 can also go with B2 or A1 with B3. Addition catches only the diagonal, right? So it misses everything else. So what we do is we multiply instead. So every A pair with every single B pair. And that gives us 3 multiplied by 3, which is the value 9. So it is a 3 by 3 grid, 9 committees in total. Independent choices always multiply, right? Okay. Now bucket K has considered it is equal to 0. So both picks from team A. So there are 3 ways to pick 2 A's and 1 way to pick 0 B's. Now, why is picking 0 things exactly one way, right? Because picking nothing is itself an option. So the empty set counts bucket K equals 2 mirrors bucket 0. Also, 3 committees, so our buckets hold 393. Okay, now if you add them up, 3 plus 9 plus 3 equals 15, right? Matches way 1 exactly. Now, watch each committee get stinted by its bucket, right? Everyone colored once, no overlaps, so nothing is missed, right? Replace the numbers with the variables. So M for team A, N for team B, and R for the committee size. Now, the same proof works for any values. And that's pretty much the Vandermonde's identity proven, right? So I hope you were able to understand. Okay, everyone. I hope you were able to understand the animation. Let me know once again in the feedback if you have any reviews or any changes that I can make. And I'll try to make any changes as possible. Okay, so now let's try to understand another theorem. And after this, we will understand another one, which is going to be the most difficult one. Once again, in this lecture, I just decided that I'll explain the theorems on the board, but I'll show the proofs using animation. It's just that the board kind of gets too messy, I would say. That's why I just thought animations might be a better way for you guys to understand. Okay, so let's just quickly understand the theorem and then I'll show the proof using animation once again. So the theorem is saying if you have Cn plus 1 comma r plus 1, then it's equal to the sum of Cj comma r, where j starts from r all the way up till n. So you can try to pause the video and just take a look at this theorem, and then I can just try to explain it. Okay, so the idea is simple. According to this, if you look at this in English sentence, it pretty much means a binomial coefficient equals the sum of smaller binomial coefficients. Okay, even if you're not able to understand this sentence, the point is very simple. You just know this is equal to this value, so you can just remember it, kind of like a formula, right? We will show the proof to explain why this formula works, but you can just remember it as well. Okay, so let's just take a quick look at one of the examples. Let's say you want to solve C5 comma 3. How do we solve it? I can write this as C 4 plus 1 comma 3 plus 1, or I should say, sorry, I can write it as C 4 plus 1 comma 2 plus 1. So according to this formula, I can say N is equal to 4 and R is equal to 2. right? So if you try to solve it, you'll get sum of j comma r, meaning 2 to 4, all the way up to c. J in this case is j um, comma r. R in this case would be the value 2. So if you try to solve it, what you'll get is just c2 comma 2 plus c3 comma 2 plus c4 comma 2. Okay, so if you try to solve this equation, what you get is you get 1 plus 3 plus 6, which is equal to 10. And if you want to verify, you can also do it using just this equation. If you try to solve this, it will directly give you 10 as well. So once again, the point is very simple. The idea is just that if you do Cn plus 1 comma r plus 1, if you do this representation, then you can do the sum of Cj comma r, okay? Which is pretty much meaning a binomial coefficient equals the sum of smaller binomial coefficients. Once again, the point is not understanding these identities. Like, it's not that you remember these identities. You can remember them. They might come in your exam. Definitely that's possible. But if I talk about discrete math in general, I'm not just talking about the exams or something, the idea is that it's more important to understand how did we come to the conclusion, how did we actually come to these formulas in the first place, right? That theory, or I should say that technique, is what the most important part of this lecture is. Okay, now let me just quickly try to show you guys the proof of this theorem using the bit strings. Okay, so it's going to be a very interesting way to show the proof. Okay, so let's understand this theorem now. A binomial coefficient equals a sum of smaller ones, right? You start with C of 5, choose 3. That means choosing which 3 of the 5 positions get a 1. So C of n plus 1, choose r plus 1, counts length n plus 1 bit strings with r plus 1 ones. This might seem confusing, but let's just understand this closely, right? Okay, so let's consider the following. For C of 5, choose 3, there are 10 such bit strings, right? And I've given all of them over here. So for every bit string has exactly one rightmost one, right? If you take a look at this, I have highlighted them with this red circle. So call it the last one. We will partition by the position of this last one. Now, where can this last one really sit, right? It cannot sit at the positions 1, 2. We need room for 3 ones. Okay, so the earliest is 3, the latest is 5, and you need 3 buckets in total. Okay, now zoom at the last position, at the position 4. So at position 4 is locked to 1. Position 5 must be 0, right? Otherwise, 4 wouldn't be the last one. Now, first 3 positions hold the other 2 ones, right? That means 3 choose 2. So, yeah, that basically means 3 ways. So, the general rule is last one at position k gives C of k minus 1 plus 1 choose R, and others check out. So, last at 3 gives 1 string, last at 5 gives 6 strings, and they both match. Okay, now the sum of the buckets, right? 1 plus 3 plus 6 equals 10, right? Which is exactly C of 5 choose 3. And that's basically the complete proof. So once again, the general sum has k minus 1 in it, which is pretty ugly, right? So just rename it. Let j equal k minus 1. So boundaries shift accordingly. So final identity, you get C of n plus 1, choose r plus 1, equals the sum from j equals r to n of c, j choose r. And we have proven it. Okay, guys, now let's understand the final theorem. This is the most tricky one of this lecture. Uh, if you can see this question, this equation on the board, it's like very tricky to understand. Even I personally spent like uh, uh, 2 hours trying to understand it, to be honest. But once again, I think it's a very interesting theorem to understand. Look, the idea is, let's just take a look at the theorem itself first, what it's saying. It's saying n square multiplied by the combination of, just wanted to clear out one more confusion. I I represent a multiplication by dot sometimes, and sometimes by the by the pretty much the multiplication sign. So I hope that's not confusing, right? Okay, so it's saying n square multiplied by the combination of 2n minus 2 comma n minus 2 is equal to this sum equation on the right hand side. Okay, so once again, the idea is that it might come in your exam, but I'm pretty sure that it probably will not. More important thing is to understand the proof technique, right? And that's what we're going to look at. Okay, so in order for us to prove this using just algebra, it will be very difficult to solve this equation, right? So instead, what we're going to do is we're going to represent each of these things as a count, right? So once we represent them as a count, then we would kind of have a story to show the proof of how it works, right? Okay, so I'm not going to write anything on the board for this one. Just wanted to show you guys this theorem, and I'll explain everything using the animation. Okay, so let's just quickly take a look at the animation now. Okay, let's do the hardest proof of this lecture, the combinatorial proof. That looks really terrifying, right? We're going to consider this example of team plus 2 captains. Okay, so the left side is n squared multiplied by c 2n minus 2 comma n minus 2. Okay, so for n equals 4, that's 16 times 15, which is 240, right? Now, combinatorial proofs need every factor to count something, right? We are basically counting in the combinatorial proofs. That's the point of using this way. Okay, so raw and square and j n minus j, they don't. We rewrite them using binomials. Okay, so watch this. N squared becomes c of n choose 1 times itself, right? J of n minus j becomes 2 small choose 1s. Now every factor counts. Okay, the story is you have two teams, X and Y, each with n players. You want to build a super team of n total players, right? And then pick two captains. So the example to track is super team X1, X3, Y2, Y4, captains X3 and Y2. And I'll trace it both ways. Okay, let's take a look at the left side now. So pick the captains first, right? And then fill the rest of the super team. So pick the X captain from any of the n X players. For n equals 4, that's 4 ways, right? So pick the Y captain from any of the n Y players. So 4 ways again, right? Independent choice. So super team needs n total. Captains fill 2 spots. So fill n minus 2 spots from the remaining 2 n minus 2 non-captains, right? And multiply the value. So 4 times 4 times 15 equals 240. Now let's take a look at the right side. Okay, so decide the team composition first. Let j be the number of x players on the super team. Then n minus j are the y players. Right, so valid j runs from 1 to n minus 1. Okay, so for n equals 4, j is 1, 2, or 3. So pick j x players, c of n choose j ways. So pick n minus j y players. Also, c of n choose j by symmetry, x captain from j x's on the team, j ways, and y captain from the n minus j y's, so n minus j ways in total, right? Okay, now multiply R4, which is j times n minus j times c of nj squared, and there's a scary right side term. Now plug in the j equals 1 and it gives you 48. J equals 2, 144. J equals 3, 148. And that in total gives you 240, right? If you sum them together. So both recipes count the same 240 outcomes, right? Just in two different orders. They must be equal, so the final identity is just that we have given, which is n squared dot c 2n minus 2 comma n minus 2 equals this sum. And hence we have proven it. Okay, everyone. So I hope you're able to understand all the three of the identities that we covered. Now, once again, they're very tricky to understand, so it's totally fine. If you have I know for University of Guelph, you guys have MCQ type questions coming in. So it's just that make sure that you remember these identities. Like I would say, definitely spend the time. Also, I would say solve a few questions for each one. Maybe like grab the identity, understand the proof, and maybe just try solving a few questions of it, right? Or I should say, just like input values into the equation and just try kind of simplifying it further, right? To get our LHS equal to the RHS. So I think that should be more than enough. Okay, so I've given these two questions on the board. Try to pause the video and just quickly solve them. Okay, so the first one is use the Vandermonde's identity with m equal n to show c 2n comma n equal this value over here. Okay, so let's just quickly try to understand this, right? I can write c2n as cn plus n comma n, right? So if you remember from the Vandermonde's identity I've given on the board, which is m plus n comma r equal the sum, I can write this as sum of c. In this case, my m would be n, my n value would be n, and obviously r will also be equal to n. So if you look at the Vandermonde's identity, this is equal to n comma n minus k multiplied by c n comma k. Okay. Now if you remember this one, c n comma k is equal to c n n minus k. These are pretty much the same thing, right? So since they're the same thing, what I can do is I can just kind of represent this as, I should say, cn comma k, which is equal to the sum of cn comma k square. You can verify this by solving a few questions. So just try to pick any value of n comma k, 5, 2, maybe 6, 3, and you can verify that c n comma k is equal to cn n minus k. Okay, second question, evaluate the following equation. Now for this one, if you remember, this is pretty similar to the theorem 2 that we covered, right? So I'm just going to skip the complete simplifying part. What I would say is you can open the theorem on the side, the second theorem that we covered, and the idea is very simple. It's just that this would actually be equal to c7 comma 4, right? Which is pretty much that you can write this as c6 plus 1 comma 3 plus 1. And if you remember in the theorem, this is how we basically covered it, right? And it's pretty much like the opposite direction that we have solved this question. So once again, if you have for your exam, you should definitely know the identities, solve a few questions of like simplification and kind of like these questions, and also have I would say just try to go through the proofs as once or twice, so just that you have an understanding of what's really happening, right? Just to get a knowledge of the technique, I should say. Okay, so that's pretty much it for this lecture. I hope you're able to understand everything. Once again, let me know in the feedback if you have any doubts or any questions, and I'll leave the Discord ID in the comment section as well. Okay, I'll see you guys in the next lecture.